This is lesson 19, which is VHDL Example 7. In this example, we'll design a 4-to-1 multiplexer. We'll also talk about the port map statement. You remember from example 17, we saw that we could design a 4-to-1 MUX out of 3 2-to-1 MUXes. Well, we just saw how we could make a component for a 2-to-1 MUX in the last example. So let's see how we can make a 4-to-1 MUX using the component MUX21C. The inputs are going to be C3 down to 0, so this will be C3, C2, C1, C0. S will have the two values, S1 and S0, and the output will be Z. So what we need is 3 instances of these 2-to-1 MUXes. We'll call them M1, M2, and M3. So we need 3 port map statements, M1, M2, and M3. Now notice we have a wire called V that connects the output of M1 to the A input here of M3, and another wire here called W, which connects this output from M2 to the B input of this MUX. Anytime you have internal wires in your circuit like this, you must declare them to be signals. So here we have signal VW of type standard logic. So there they are right there. And now, remember in the port map statement, the values on the left-hand side here, A, B, S, and Y, are the component names. That's the name of the component that we had for the 2-to-1 MUX. So each one of them has A, B, S, Y, A, B, S, Y. And we just have to wire them up. So in this case, remember the 0 input's A, the 1 input's B, and in this case, S0 is the S. In this case, S1 is the S. So here we have A gets connected to C0, B gets connected to C1, S gets connected to S0, and Y gets connected to V, the signal V that we declared up here. For the second MUX, M2, its A gets connected to C2, its B gets connected to C3, its S gets connected to S0, and its Y gets connected to W. And finally, the last 2-to-1 MUX, M3, now its inputs are V and W and the output Z. So its A gets connected to V, the signal V, B gets connected to the signal W, S gets connected to S1, and Y gets connected to Z, the output Z. So you see in each case the component names are the same on the left-hand side of the port map statements, and inside on the right you just wire it up to whatever inputs, outputs, or signals they get connected to. Now it's easy to get those port map statements. You remember when we right-clicked on the component MUX21 here, before we took this component declaration and could paste it into here, now you can, if you right-click on here, you can select Copy VHDL Instantiation, and if you paste that where you want the port map statement, it will give you the template of the port map statement with all of the component names on the left-hand side as the correct ones. They'll also be on the right-hand side. In general, you'll need to replace those with whatever inputs, outputs, or signals they get connected to. Here's the simulation of that program. We used a binary counter for C, so here it's the value 6 and 9. We incremented it by 3. So here's C3, C2, C1, C0. And then we made S a binary counter going 0, 1, 2, 3, 0, 1, 2, 3. So when S is 0, then Z should get whatever C0 is, in this case 0. We also show the signals V and W. When S is 1, then Z is C1, which is 1 here. When S is 2, then Z is going to get C2. And when S is 3, Z will get C3, which is 0. And then these values change, so now when S is 0, Z gets C0, which is now 1. When it's 1, it gets C1. When it's 2, it gets C2. And when it's 3, it gets C3. Okay, well that's how we did it using port maps. We could, of course, expand this logic equation like we did in example, the last example in lesson 17. And we could actually write a VHDL program, same C, 3 down to 0, same S, 1 down to 0, same output Z. But now we'll just write the logic equation Z in terms of the logic equation, not S1 and not S0 and C0, or not S1 and S0 and C1, or S1 and not S0 and C2, or S1 and S0 and C3. And that would produce the same simulation, same waveforms we had before, exactly the same. So it works in either case.